Okay, so let's start. Today we'll talk about PRGs for regular real-world spreadsheet programs. Okay, so today we're constructing PRGs for regular real-world spreadsheet programs. Regular means that the in degree of each vertex is 2. Okay, so usually each vertex has a 0 and a 1 coming out, but here we also demand that the in degree of each vertex is 2. It could be like each vertex outputs 1, this vertex outputs 1, if it's also anything about the out degree. So the out degree is always 2. And in a regular program, the in degree must be 2. And why do we care about these objects? Because there is a reduction that shows that optimal PRGs for regular program imply optimal PRGs for all ROBPs. Okay, so this is our goal today. And in order to analyze these objects, we'll define another model called ROEP, where E stands for evaluation. And model is there, and everything works the same. Just in the end, instead of set states and reject states, each vertex has value QB, which is 3. And what's a PRG for ROEP? So it's a set S, set expectation of f of s. So what's f of x? So we follow the track that's defined by x. You get to ux. Okay, so the expectation of f of s is expectation of. And let me omit the expectation. Whenever I write f with capital letter, it will mean expectation over the capital. So this should be process. So this is and okay, so note that PRGs for ROEPs imply PRGs for ROBPs because we can simply take the ROEP, which assigns the value 1 if we're in an accept state and 0 in a reject state. Okay, so this is a generalization. And okay, so we now extend the definition of these Qs, and we derive for vertex U in the other layers, like QU equals the expectation of the program that starts in the vertex U and go to the end over the uniform distribution. What do I mean? So I start here. I proceed by a random walk. Okay, so I can start here. QU has like it's already defined. It's like no. So in an ROEP, you assign values to the last layer only. But now I extend the definition, so there will be Q for the vertices in the middle layers. Okay. So QU is for middle vertex is the expectation. So I start in U and I take a random walk if 0 and 1. And I just take the expectation of the result. Okay. Let's define the weight of a vertex. So let's take a vertex here, one for the last layer, and say it has a 0, 1 that go to QV into QX, and say QV and QX are close to each other, means that it doesn't matter if my last bit is 0 or 1, I get approximately the same result. Okay, so this quantity is sometimes called the importance of a vertex B, or the weight of a vertex B is Q V received by 0 minus Q V received by 1. Okay, so means how important this step is. Okay, because the difference between choosing 0 and 1. And you know the weight of F by the weights on the left. Okay, so for warm up, let's move the lemma about this model. We prove that for every x and y, f of x minus f of y is at most the weight. Okay, so the size of the range of f is bounded by the weight. Any questions? Okay, so how can we do this? We prove it by induction. So let's start with the base case. So f is just fixed out and 0 to 1. So the only possible inputs are f of 0 minus f of 1. Wait, question. What's V in V? What's V? V is not the vertices in the entire graph. Okay, so what's V 0? Be like this one? Yeah. So it says you are to build it's V, and then you take a step and then 0 there. Okay. Okay, so this is the most, but by definition, it's the weight of the start vertex. The most the weight of that. Okay. Now for the step.
That's the why is that? That's most of the weight of F because the weight of F is the sum of all the weights.
Okay, so in the general case, so we have f of x minus f of y, and we'll look at the branching program. Right, we have now n layers, and by induction we know the this lemma for length n minus 1 programs, and call this program fl. Okay, the left side of the program. And we have some x and y. And let's call this one Vx and this one Vy. And let's write this one as f of x minus. That's y plus q y minus f. This is just the binary quantity. Now this one, how can I bound this one? We see the most the weight of f there by the induction hypothesis, right? Because these are values that come from the left side of the the branching formula. We just apply the hypothesis. And for these, so we only have to open this term. So f of x minus the x, what's q dx? So
It's the step before the ones, right? So
Vx is this one, yes. So what's the value q for this vertex? So this one is the expectation over the uniform continuation. So it's half f of x plus half f of x1 to the xn minus 1, and then flip the last bit. Right? And this is exactly okay, so the 1/2 cancels, and it becomes half the weight of the vertex. Okay, and then so this is the closed half the weight of the x, and this is half the weight of the y. And altogether, these are less than the weight of them. Okay, so bottom line, the range, the size of the range of an ROBP is at most the weight the ROBP. Okay, let's move on. So now we're more familiar. Now we're more familiar with our own EPs, and we'll prove some things about them. So one will show a PRG or bounded weight or low weight. Or EPs. And two, show that. So we'll show that regular ROBPs, when we think of them as ROEPs, must have low weight. So that regular implies low weight. Let's say so the second item is not very interesting. We'll do it if we have time. But the first one will show that actually we already know this this PRG. We'll just show a proof that it pulls low weight ROEPs. So the INW PRG pulls on F, the weight of F equals M. Epsilon pulls such functions, such ROEPs, and we need a seed length of log n times m. Okay, instead of the
that's what we're going to show.
yes, what we've seen in class is that instead of this m we have m. So note that the length doesn't matter in this term only. So the weight is the thing that actually plays the important role. Okay, so do you remember INW generator? So it's a recursive generator. You take, like, you start with an X, and then you take a random step on an expander, and then you apply it again. Okay, so we start with a lemma. A priori has nothing to do with these generators. It's more general. So let's say we have F 0, 1 to the n. And what we are going to do is to like split F to two parts, the left side and the right side, and then show that each part is full, then the correlation between the seeds doesn't. Okay, but let's forget about correlations. So define FL of X is just F of X. Okay, so this is when we start by plugging X and then take the uniform random walk. And the second part is a family of right side functions, which is the form FA equals A. So this one. Okay, so a family of function which fix the first half of the inputs, and then the input is the instructions for the half of the second half of the work. So if xn epsilon n forms xn and xr epsilon r equals the family fr, then xn xr, when these are independent, pull this is what we want to pull first, and then we'll have to take care of the correlation between XL and XL. So how do you suggest we do it? Let me omit the expectations again. And XL XR minus uniform. What do you suggest? Like a hybrid argument. So XL uniform minus X and XR, X uniform plus X uniform minus okay, so how do I bound the first term? So the second term is just, this is the definition of FL of X, and this is the definition of FL U. Actually, because I omit the expectation of things. Okay, so the second term is the closest epsilon there. In the right term, I can take the, if we always do it, we take the fix XL. Okay, do you want to write it? So the second term, this one, is, let's write it explicitly, excitation over XL and U F XL and U minus sorry, it's out. Okay, now we can, this is at most take the expectation over Excel outside.
XL is like the output of the INW, right?
For now, we're only proving the lemma. Don't think about
XL is just some distribution.
Yeah, so XL folds epsilon L folds FL. Okay, so this is at most like the triangle inequality. We take the expectation over XL outside. And then inside the absolute value, we have fixed XL. So we can call it F XL, like these ones. It's from this family.
So it's just most epsilon now.
Yeah, exactly. And so choose it. Now, epsilon L plus epsilon. Okay, so this is the lemma for the uncorrelated seeds for the two parts. Okay, but what we want to do is to take okay, I write it now.
That's assuming you assume here somewhere that they're independent XL and XL.
So the triangle inequality is true. Also, it's dependent. And so yes, I think here, well,
When you split it up to the two,
oh,
yeah, you need to assume that it's a multiplication, like מכפלה.
yeah, in order to take the expectation outside from the absolute value. Yeah, I think so. Okay. Okay, so now let's see what we really need. So assume we have a PRG which takes seed and outputs n/2 bits. And our new PRG is going to be g of x and g of y. Well, x is uniformly random and y is a random neighbor of x in an omega expander. Okay. So there are parameters W in the background and everything as always. And we'll show that these full F. Okay. So G was all F. L epsilon times the weight of it. Okay, why do I need the weight of it here? Because in every ROEP we can just multiply all the Q's in the last layer, and then they are just gross linearity, because it goes through the linearity of expectation. Okay, so this is the right way to measure the PRGs. Okay, so assume this, then this PRG pulls all F with no epsilon plus W times omega, the weight of it. Okay, this one is for length n/2 ROBPs, and this one for length n ROBP. And this is the loss in the error. Okay, this is what we are going to do. So let's do it as always. So we need f of g of x, g of y, compared to f g of sorry, f let's split it into two parts. So first g of y minus f of g of u, g of u prime plus u of u prime minus f of u. Okay, so in the first term, I handle the correlation of x and y, and in the second term, I handle the errors, the PRG. So let's bound the second term first. So this is the lemma with force before, okay, because these are uncorrelated. I mean, they are independent. Okay, and G on U pulls, I mean, G pulls the left side, right? Because it's a length n/2 ROEP. So it pulls the left side with epsilon weight of the left side, and the right side with epsilon times the weight of the right side, which is at most epsilon times the weight.
It's just equal, no?
Uh,
Maybe if there's uh, like a layer in between this and both of them, it's
yeah. Yeah. Okay, so this term is easy. Let's talk about this one. So here comes click. So I want to recall that what we did is to take the layers and then condition on the vertex in the middle layer. Right, so I want to add f of xy as sum over all v in the middle layer of f from the beginning to the x times f from b to the end of 1. Now let me explain these terms. So this is always 0, 1, and it means I start in the starting the f. I follow x, and if I reach v, this gives 1, and this one is the half. Okay, and, starting from V, following. Okay. So this is the V. It has V star, the same as the one of F, and it has a vertex V here, and this is like this has the value 1, and all the others have the value 0. Okay, and this is actually an ROBP. The V is the accepting state, and all the other non-injecting states. And this one starts in the vertex V and follows the instructions Y and finishes in Q like starting from V and then so it's something. Yeah, for fixed. Okay, so now let's talk about the expander mixing grammar. So we want to claim that if we plug G of X and G of Y, we're going to get something similar to when we plug G of U and G of U prime. Right, that's we need to bound this term, plugging G of X and G of Y instead of G of U and G of U. Okay, now X is uniformly random. Okay, so X and U are the same, but it's just what is X uniformly random? Oh, right. Okay. So for a minute, think of these functions as okay, so let me just F compose with G in both of them. And then we just need to plug X and Y and U and U one. Right? Y plus U and U one. Okay, so for a minute, think that that this function is also the 0, 1 function. So when is this 1? Only when both of them are 1. Right? So we have like, let's call this one is H, and this one is two different functions. So we have a region where H equals 1 and a region where G equals 1. And the expander mixing lemma says that if we sample X uniformly at random and then sample a neighbor Y, which is equivalent to sample an edge in the graph, then the probability that the edge goes between these areas is as expected. It's like size of this set, the density of this set times the density of this. Okay? Like mu of H times mu of G. What we need now is a slightly more general statement, which says that we have two functions. We have the vertices of the graph, and we have two functions, H and G. And G will be red. And H gives some values, say 1, 2, 7, 5, 12, 2 to the vertices, and G also assigns values to the vertices, 0, 3, 1. H gives 0, 1. Yeah, we'll now prove a more general statement. Okay, and we sample an edge. We'll get that sample an edge UV. We'll get that H of U times G of V is still approximately mu of H times mu of V. Okay, this is a more general statement when the H and G are not necessarily 0, 1 value. Okay, and the proof actually is identical to the proof of the expander mixing lemma. Okay, so we have, let's write it as H transpose times M for W. D. Okay, so we write it as the I plus J plus D. Okay, so it's H parallel exposed times J times G parallel plus H parallel exposed times H times G parallel. Okay, because J acts only on the parallel space, the O1 vector, and E sends to zero on the parallel space, so we are left with the perpendicular space. And this is exactly mu H times mu G. And this is at most, so it's the omega times, omega is the spectral expansion of the graph, times the norm of H per, times the norm of G per. And this is a plane, and then simply the variance of H square root. Okay, because we take the square root of all the squares, the norm is the square root of sum of H squared. But watch H per V, it's like HV minus U H. Well, and this is like X minus expectation X squared, which is just the definition of the.
So it's omega square root variance of X square root variance of G.
Yes.
Okay, that's right.
Okay. So let's call it the sigma H times standard deviation. So what do we know about the let's plug our H and G. What do we know about the standard deviation? Oh, one more important fact is that sigma H is smaller than size of the range of H.
It's just Poynting function.
Yes. Yes, the standard deviation cannot be larger than the support size. Okay, so for H, this is at most 1, right? So which bound will I use for G now? Weight of it. The weight of it, yes. Right, because the range of G is the range of F. And the range of F is bounded by the weight of F. That's what we call in the beam. Okay, so we found F of G is I minus F of G mu prime. And now that's condition on the vertex in the middle. So we need to say that if y equals sum of f, sum over all v, oh, we said it before, right? V times f from v to the n. So using the line inequality, we condition on v and write that O to G X O to G this minus the same, but with u prime. And this is simply mu h times mu g. Right, because this is just like sample 2 points at random, and this is how far is it from this term? This is at most. So we have omega times the variance of this, which is at most 1, times the variance of this, which is at most with most omega times w times the weight. Very confusing. W. Okay, so I think that's it, right? So we needed to bound this term. We split it to these two terms. The first one was easily bounded, and now we bounded the other term by omega times W times weight effect. And this finishes the move of this statement. Okay, so the IMW generator pulls. So we still need to do the calculation of the accumulation of the error. So how does the error accumulate? So in each step, we add an error of omega times W. So in the end, we have an error of log n steps times log n steps times each step has omega times W times the weight of F. And we need this to be smaller than epsilon. Right? So now we can choose omega. Okay, log n steps. In each step, we add a factor of omega times W times the weight of F. And we need this to be smaller than epsilon. We need to choose omega equals epsilon over log n times W times the weight of F. Okay, let's substitute it with log n times omega times W times m, because m is an upper bound for the weight function. This is m. Okay, and now we need to choose d accordingly. D is the degree of the graph. So we need to choose d, which is approximately 1 over omega, maybe squared, but this is all going into a log. So why do you need d to be 1 over omega? Because I need an expander, an omega expander. Yeah. So I need d equals 1 over omega squared. Right? Because we have omega equals 1 over square of d. Approximately. So we have this, which is log n times omega times W times m over epsilon, and then we take the seed length. What's the seed length? Log n times log of d. So all in all, it's the seed length is this expression when this log n becomes log n and goes into the 2. Okay, so INW generator pulls low weight ROEPs with this seed length. Okay, we don't have the time to prove that regular ROEPs are must have low weight as ROEPs. But the proof is not really interesting, so it's okay to skip it. I'll just state the result there. So for every one set every regular ROBP has weight most W squared. Okay, so the weight of a regular branching program does not depend on the length, although we had more layers with more weights, and it only depends. It's bounded above by the width of the program. Okay, plugging it back here, we have that the INW pulls regular ROBPs with modular of log n times log of W, which is better than what we proved before, right? We proved the factor of n. That's it for today.
The proof, we didn't use the regularity, right? You use it when you want to show that it's slow wave.
Yes,
So we didn't use it.
yeah. Any more questions?